We have done a lot of groundwork on this problem of heat transfer through a fin when we looked at the boundary value problem. We are going to consider the same system, but now with a different set of conditions that are specified. Remember, we remarked that since this is a second order ordinary differential equation, we would need two conditions specified in order to solve the problem. For the boundary value problem, one condition was specified at the left boundary and one condition was specified at the right boundary. So we solved that using the BVP4C and associated commands. Now here, let's say we are given the two conditions, but both conditions are given at the same value of the independent variable. That means both conditions here are specified in this example at x is equal to 0. So you wanted two conditions, both the conditions are specified, but both conditions are specified at x is equal to 0. This makes for what is called an IVP or an initial value problem. So in this case, the governing equation is the same. There is no change with that, but the conditions specified differ in this condition. The first condition is the same as we saw before in the boundary value problem. At the base of the fin, the temperature is equal to T naught. In this initial value problem, the second condition is specified in terms of the gradient of the temperature, right? What is the gradient of the temperature at the base of the fin? The gradient at the base of the fin is given as this expression, minus T0 minus T infinity by L. So when this is specified, we will see how the problem formulation and its solution changes. The problem has not changed, so we are going to look at the dimensionless temperature again as we defined previously. We are going to look at the dimensionless position as we specified before. Using these, we knew that we could reduce the problem in terms of theta and psi as this. Remember, we also specified HPL squared by Ka to be equal to 4. So all those things don't change. So the governing equation doesn't change. The definition of the dimensionless quantities doesn't change. And therefore, the new differential equation in terms of dimensionless quantities is the same as we saw for the boundary value problem. If you look at the first condition, the first condition is the same, and with the dimensionless quantities being exactly the same as before, the first condition also remains the same. So we get this to be the condition for theta at psi is equal to 0. Now the second condition is specified as this. So please pay attention to this. The second condition is specified as this. And now what we realize is if theta is equal to this expression, we can write t as T naught minus T infinity multiplied by theta. This goes from the denominator to the numerator, so it multiplies. And this minus infinity goes to the other side, so it becomes plus infinity. So T in terms of T naught, T infinity, and theta using this expression comes to this. So T is equal to T naught minus T infinity times theta plus T infinity. And then when you apply derivative on both sides, so you do d, the derivative operator on both sides, you get dt on the left hand side. On the right hand side, we know T infinity is a constant, so the derivative of that is 0. T naught minus T infinity is constant because of our assumption, and therefore T naught minus T infinity can be pulled out and you get d theta. So dt is nothing but T naught minus T infinity d theta. We also know that x can be written as psi times L or L times psi. And if you apply the differential operator on both sides of this equation, you will get dx is equal to d of L psi. And since L is a constant, you can pull it out and write dL psi as L d psi. So dx is going to become L d psi. So you take this dt and you take this dx and you create dt by dx on the left hand side. On the right hand side, you will see T naught minus T infinity by L d theta by d psi. So this is what you will get. So this is specified in the problem to be equal to, this is the what is stated in the problem. So minus T naught minus T infinity by L. This is what is stated in the problem. And therefore, if you cancel out T naught minus T infinity and L on both sides, you get d theta by d psi is equal to minus 1. So at psi is equal to 0, d theta by d psi is equal to minus 1. So basically what we have at this stage is that this is the differential equation governing the system based on conductive and convective heat transfer mechanisms for the fin. And the conditions required to find out theta are given as theta and d theta by d psi, both at psi is equal to 0. So theta is given to be 1 and d theta by d psi is given to be minus 1. So this is something that I've just described. And let's take HPL squared by Ka equals 4. If you remember the notation we used in the boundary value problem, we have to convert this second order ODE into two first order ODEs. So we introduced two symbols, as you may recall. Z1 is equal to theta, the dependent variable. So the new symbol 1, Z1, is equal to the dependent variable. In this case, the dependent variable is theta. Z2 is defined to be dz1 by d psi. And since z1 is also equal to theta, to keep consistent with the earlier notation, we will have z2 equals dz1 by d psi, which is also equal to d theta by d psi. So wherever I see d theta by d psi, I can use z2. If I see d squared theta by d psi squared, I can say that is equal to dz2 by d psi. All right. So basically what happens is from the definition as we looked at when we discussed the boundary value problem, we can write dz1 by d psi is equal to z2. So that gives our first ODE. The second ODE is going to come from the governing equation, not from the definition, but from the governing equation. So I can replace d2 theta by d psi squared as dz2 by d psi minus HPL squared by Ka, that is equal to 4. Theta, theta is nothing but Z1 equals 0. Therefore, dz2 by d psi is equal to 4z1 as we wrote before. So we have the same two differential equations as we had for the boundary value problem. Since the equation doesn't change, we don't expect the ODEs to change. So I need not have elaborated this, but for the sake of completeness, I did it. So we get the same two ordinary differential equations that describe the system. Now, the first condition given to us is theta at psi is equal to 0 is 1. We know theta is nothing but z1. Therefore, this translates to z1 at psi is equal to 0 is equal to 1, right? So that is what you get here. The second condition is d theta by d psi is equal to minus 1 at psi is equal to 0. So both conditions are at psi is equal to 0. That's why it's called an initial value problem. Both conditions are given at the same left boundary, which is psi is equal to 0. So in any case, d theta by d psi we know is equal to z2. So z2 at psi is equal to 0. So z2 at psi is equal to 0 equals minus 1. That is the status of the problem now. These are the important things to focus on right now. And again, we are interested in z1 because we are interested in theta. We want to find out theta as a function of psi. You will solve it, as I will show later, with this function in MATLAB called Ode45. So there are a few MATLAB routines, Ode23, Ode15S, and Ode45. These are the three commonly used routines for solving initial value problems in MATLAB, out of which the most popular one is Ode45. But sometimes, as we can see later, there are some peculiar cases called stiff systems where ODE45 will not work well. And in such cases, we can try our luck with ODE15S. This S stands for stiff solver. That means certain differential equation systems are called stiff systems because of their nature. We will describe that later when we get to it. So these stiff problems cannot be solved using ODE45. They can be solved with ODE15S. So the main things to remember are ODE45 and ODE15S. So what's the MATLAB code? So I'm just showing the M file that I've written. It's quite easy compared to the boundary value problem. So basically I'm calling ODE45 And I have to tell ODE45 what is the name of the function file that contains the ODEs. So we need to know that. The next thing is, what is our starting value of the independent variable? What is the ending value of the independent variable? So here the independent variable psi goes from 0 to 1, and I want to break it into 100 parts, this domain into 100 parts, right, to get a smooth curve, etc. So I start at 0, which is the left boundary, that is the base of the fin, and go in steps of 0.01 units to the tip of the fin, which is psi is equal to 1, which is the right boundary. So this is what is called the span of the independent variable. And then I have to give the initial conditions. So three things: the name of the ODE file, the span of the independent variable in square brackets, and the initial conditions in square brackets again. So we know that for Z1, the first symbol, the initial value is 1. Can you see this? So for Z1, the initial value is 1. For Z2, the initial value is -1. This is what is specified in the problem. Therefore, I use 1 and -1. So this is the initial condition for state 1 or for symbol 1. This is the initial condition for symbol 2, which is Z2. So I specify that. So ODE45 processes the differential equations found in FinODE function, and it uses the span of the independent variable, and it uses the initial conditions that are specified in the problem. So the outputs from ODE45 are stored in XX. So XX contains the values of the independent variable. YY contains the values of the dependent variable at the value specified in XX. So here YY will contain, in this problem, YY will contain two columns. The first column will be Z1, the second column will be Z2. So if you're solving a fifth order ODE, you would have 5 symbols: Z1, Z2, Z3, Z4, and Z5. In which case, YY would contain 5 columns. The first column for Z1, the second column for Z2, the third column for Z3, the fourth column for Z4, the fifth column for Z5. So you can pick and choose whichever column you want to plot. Here we are interested in theta, which is Z1. We are not as much interested in this problem in d theta by d psi, which is nothing but Z2. So we are not interested in Z2, we are interested in Z1. So we are interested in the first column. And that is what we will plot. Before getting into that segment of the code, I just want to say that the FinODE file is exactly the same as we wrote for the boundary value problem, because the differential equations don't change. So it is exactly the same as we wrote in the boundary value problem. So kindly take a look at that video to find out how this function is constructed. So in the same M file, all of these are there. So in the last portion of the M file, I have this function, right? FinODE, the same name as you see here. So I'm not going to describe this part because we have already looked at it at length. So when ODE45 is called, it will come to this FinODE. It knows what differential equations it has to solve for which span of psi, and what are the initial conditions for Z1 and Z2. So once it solves, then we can open up a figure window, graphics window, by typing figure or saying figure 1. So it will open up a figure window 1. All right. So in that, I'm going to plot on the x-axis, or on the horizontal axis, I'm going to plot the independent variable. And on the vertical axis, I'm going to plot Z1. So as we remarked earlier, this is YY. We are looking at the first column of YY. So therefore, I'm going to plot YY colon comma 1. This colon is the index for the rows. So I want to plot all the rows. So I say colon comma from the first column. So plot XX comma YY brackets colon comma 1, and I want to plot it in black color. That's my choice. You can plot it in magenta or red or green or whatever color you choose to. So this is the plot command, and basically I can use the X label command and Y label command to specify the labels that I want to see on the graph. So when this M file is saved and it is executed, we are going to get this graph. Okay, so kindly note that at psi is equal to 0, theta is equal to 1. We have not plotted the second column of yy. Otherwise, we would notice that the value of z2, that is d theta by d psi, at psi is equal to 0 would be -1 as required in the problem. So this is how you can solve initial value problems. Now, before closing, I just want to say that the initial value problems are what are called marching problems, because all the conditions required to solve the problem are known at psi is equal to 0. It's all known. I know theta at psi is equal to 0. I know d theta by d psi at psi is equal to 0. Using that information, I try to solve for theta and d theta by d psi at psi is equal to 0.1. Let's say that's the next point. So I can use the information at psi is equal to 0 to solve for the theta and d theta by d psi at psi is equal to 0.1. Once I do that, I can use the values at psi is equal to 0.1 to find out theta and d theta by d psi at psi is equal to 0.2, and so on until I reach psi is equal to 1. So this is what is called a marching problem. So we can solve it sequentially. From psi is equal to 0, we can find out the solution at psi is equal to 0.05, let's say. Then using the solution at psi is equal to 0.05, which we just found out, use that as a base to find out the value of theta and d theta by d psi at psi is equal to 0.1, and so on until the end point that we choose. So this is a marching problem. Whereas the boundary value problem was fill in the blanks problem. We are not able to march like this, right? So we have to assemble all the equations there and solve it simultaneously. So initial value problems can be solved as sequential approach, whereas the boundary value problems can be solved using a simultaneous approach. That is how it is typically done. So let me stop here and catch up with you on a different video.